Alright, in this pre-lecture video, I chose to talk about the measurement devices that we might use in a circuit. I know that you did a lab dealing with ammeters and voltmeters, and I also am going to spend more time in class concentrating on RC circuits, so I thought this was a good place to do this. So basically, we start off with the idea of a galvanometer, because the galvanometer is something that is contained in most ammeters and voltmeters. In fact, as you'll see in this little mini lecture, and also as you saw in your lab, you can use a galvanometer in different ways to actually function as either an ammeter or a voltmeter. So when we're using the galvanometer, one of the things that is important is the idea that when current flows through the galvanometer, it actually is used to do measurements because the needle will deflect in a way that's proportional to the amount of current that's flowing through it. We use the idea of what we call the full-scale deflection, and we are going to call it the IFS, is the current that's flowing through the galvanometer when you have the full-scale deflection is IFS. Now, in the way that we might use this, or something that's useful for us to know, is of course the coil is going to have some resistance, and we'll call this R sub C. And then if we are measuring the full-scale deflection, the current that might go through it in this point is actually usually pretty small. So for instance, we might find that our galvanometer undergoes a full-scale deflection when a current of 1 milliamp goes through it. If the resistance of the coil is 20 ohms, then this means that the potential difference across the galvanometer in this case can be found from Ohm's law, which will be equal to 0.02 volts, and this will also be referred to the voltage at full-scale deflection. All right, so we're going to talk about ammeters and voltmeters. The ammeter is the device that's used to measure the current passing through it. So it's what we would use to figure out how much current is in a circuit, while a voltmeter is going to measure the potential difference between 2 points in the circuit. And as we'll see, we can talk about how a galvanometer could be used to measure or to create both of these instruments. First of all, we should be familiar with the idea of how an ammeter is supposed to be used in a circuit to measure the current. And when we want to measure the current in a circuit, we literally want to break the circuit and insert the ammeter into the circuit so it's in series with everything else. So in this case, we're looking at the battery. The light bulb, remember, will be like a resistor, and then here we see the ammeter, and it's in series with everything else. Now, if you think about it, if we want the ammeter to not affect the current that it's measuring, then we want its resistance to basically be 0, because if it has any other resistance, that would change the overall resistance of the circuit, which of course would then change the current. And so that's why we would want, in an ideal situation, the resistance of the ammeter to be 0, or at the very least to be as small as possible. Now, if we want to use a galvanometer to work as an ammeter, as you saw previously, the current that the galvanometer can handle, the I full-scale current, is actually pretty small. And we would find that in most cases, the current that we want to measure is going to be probably pretty big compared to that full-scale deflection current. And so what we can do in order to use our galvanometer to work as an ammeter is we actually will connect what we call a shunt resistance in parallel with the coil resistance. So we're sort of adding something to it. What this means is that the shunt resistance will allow some of the current to flow through that, and because of the fact that there's only a limited amount of current that can flow through the coil because of the fact that it can't really handle too much. So the IFS current is that's going to go through the meter, and then the amount of current that goes through the shunt would be the total current, which we'll call I sub A, minus the IFS. And this is what's going to go through the shunt resistor. Because of the fact that the potential difference across both resistors, the resistor of the coil and the resistance of the shunt resistor, because they're in parallel, they'll have the same potential difference across each of them. And so we could say the potential difference across the coil would be IFS times the resistance of the coil. And that would be the same as the potential difference across the shunt resistor. This is going to help us figure out, for different situations, how big would we want that shunt resistor to be, depending on how much current can go through our galvanometer and what kind of current we're trying to measure. Now, if we want to use a voltmeter, when we connect a voltmeter to a circuit, we literally sort of take its two connections and use them as probes to find the potential difference between 2 points in the circuit. So for instance, in this picture, this voltmeter is being used to measure the potential difference across the light bulb, which of course is going to act like a resistor. In this case, we want the resistance of the voltmeter to be very high, maybe we should say approximately equal to infinity. We want it to be high because if it's a high resistance, not much current will flow through it, because again, the idea is that if you have current flowing through the voltmeter, it's actually going to affect the current that's going through here, and then of course it's going to affect the measurement that you're trying to make. If we want to use a galvanometer as a voltmeter, what we do is we're going to connect a resistor in series with the galvanometer. And then if the full scale reading of the galvanometer is, we'll call it V sub V, then what's going to happen here, see we're trying to measure the circuit element, the V sub V is going to be equal to the full scale current times the resistance of the galvanometer plus the resistance that we've put in series. And what this will do is most of the potential difference is going to be across the resistor that we put in series, not the resistance of the coil, and that's going to help us out. And so that's really just some little facts. Probably or hopefully you learned a lot of this in lab, but I wanted to at least have the opportunity to cover it since we probably won't do it in class.